Welcome, developers. Let me start with my humble apologies for keeping you waiting. I've been busy with a lot of things, not just that AI video that I put out, but also lots of retries on this video and doing some studying and testing with tools for making those kind of videos. So I hope it will go faster from now. In this fourth installment of Programming with SimConnect, we're going to be moving from C to C++ with respect to getting data from the simulator. However, this opens up a subject that we've managed to stay away from, and that is that of our application's architecture. I'll use some examples from C# to explain why I think this is important, whether you're planning a WASM plugin or a standalone application. So let's go. My goal for writing the C++ library has been one mainly of usability. How can I make calls to SimConnect less verbose? How can I provide helper classes and simplified calls? And what tasks can I delegate to a library because it's always the same? I'm a bit of a programming language and reusability nerd, so I use the types from the standard template library a lot. And I also make use of all those great language features that C++20 provides, as I've already discussed. I also have a few convictions that I'm afraid I'll apply to this. I think many new C++ features have a bad reputation that is undeserved. So if I can split work between preparations and later, I will actually accept extra work during preparation if it makes the later acceptably fast. Hardware is nowadays pretty fast, so you tend to overestimate costs in time. There is an effect here also at play that I'm calling the curse of the library designer. Especially in C++, people tend to sacrifice a lot of usability to speed. You often hear, "I want all the features, but none of the overhead." Effectively, this means that you won't see some features in C++ that are common in languages such as Java, C#, Python, and JavaScript because they are considered too expensive. For example, being able to scan a class type, discover the fields, their types, the names, and then retrieve and assign values to them using that information at runtime is called reflection. Java had this from the start. At runtime, C++26 is going to finally get it, but only in a limited fashion and only at what is possible at compile time. When receiving data from the simulator, I want to use types fitting my program, not types that XP-era SimConnect wants. This means I can often not map a struct or a class on top of the data. Also, if I want to generate code to automatically assign simvar values using annotated code, I have a problem. In C#, using the C and CsSimConnect library, I can do this. Each field in this class has an annotation, it's called an attribute in C#, that specifies the simulation variable, the transfer type, and can also specify any other details needed. Then, when actually calling the requestData method on the data manager, it will use reflection to extract that information from the class definition and at that moment build the data definition block. It also generates efficient getters and setters that can convert values to fit the field's real type using lambdas. By the way, you'll note that after sending the request in this example, I immediately call a method called get and assign the result to my variable. This sounds impossible because we need to wait for the right message to come with the data, then extract the data, and then assign the result. In C#, this works because we have a multi-threaded environment. A separate thread, while my program is running, handles the communication with the simulator. It also takes care of all incoming messages and dispatching them to wherever they are needed. This means I can block the current thread. And then when the data is available, the value is constructed, extracted from the message and constructed, and then passed on as a result of the get call. So then the thread can unblock and continue. Now in C++, I cannot use runtime reflection. So how do I tell the library about my struct? What I've done in the library is to use a data definition object that collects this information. So the information that in C# was implicit and extracted at runtime here needs to be explicitly passed to a data definition object. This works because the template function that can generate those lambdas, just like C and CsSimConnect, to get and set values and even convert between types. And because it's a templated method, it can do this at compile time. The library code looks horrible if you're not used to it, but it's surprisingly efficient. It has alternatives that let you provide custom lambdas if you need special handling. I've even added detection for straight-on mapping when possible. But for that, you need to have exactly the right types in the fields and use, of course, no variable length strings. But if you don't trust me, there's also a way to simply ask the request method to call your lambdas to extract the data from the message instead. So what now happens is that you get the request handler, enable the SimObjectData messages for it, and then request the data, in this case requestData once. And it's a templated method again. It gets the class, and then you get a lambda as parameter, or you pass a lambda as parameter that will pick up the data and do something with it. And this is your class that already has passed into it all those values. But this is not everything. You can use different types of add methods to make those fields known. The first one is simply called add and is a templated method for all the different field types, where you explicitly specify the SimConnect data type. And of course, you pass as a parameter the simulation variable and the units, which is defaulted to an empty string for when you expect a return of a string. An alternative is to use the add int 32 or whatever other type there is, for example, add float 32 or add string 8 and those kind of methods, which thereby determines the type of the field. So here the type of the field is explicit, but still you pass in the simulation variable and the units. In both of these cases, the method will generate those getter and setter methods for you. If you don't want to do that, you can also do it explicitly. Here you have two versions. The first one, in this case for an int 32 bits, gets a setter where the method that extracts the data from the message passes the data to this lambda that you pass, so you can do with it what you want. The other way around, if it's for set data rather than get data, you can use a getter, which will return the value that needs to be put into the message. The alternative is that you just pass a struct because you do want to use the struct, but you want to determine how it needs to be converted into the correct field of that struct. In that case, you can explicitly pass the lambdas for that. The first one is to put the value into the struct. The second one is to extract the value from the struct. I've also added a request class to the library. Objects from this class are returned by the requestData methods. When a request object is destructed, it will clean up the request. So if you have a request that gets multiple times delivered the data, you keep this request object. And when you say, okay, I don't need this anymore, I want to stop the simulator from sending me the data, you can either delete that object, let it go out of scope, or explicitly use a stop method on it. If it's just a once, then probably you'll have a lambda that you passed into the request method, and that lambda can then obtain that request and use it. So why did I put all this into my design? As we've seen in the previous episode, when you request data from the simulator, you can tell it to send that data once, or let it continue sending until you tell it to stop. So because of this, we get a situation where we may be unable to predict when, how often data will be coming in. We cannot even know for sure what kind of data will be coming in, because there might be multiple requests going at the same time. And at the same time, our application may have other things to do. For example, we may have a UI that needs responding to user input, or we may have network connections that need to be monitored, or hardware connected to the computer that sends interrupts that we need to do something with. Or we could have simply long-running computations, and we want the work on the messages to be done as the computation is going on. In our code example so far, we sent some requests and then more or less sat back and just listened to whatever the simulator sent us. Because we now potentially have multiple streams of data coming in, as well as other work, this approach doesn't work well. We need some way of dividing our attention between those tasks. The obvious approach, of course, is to use multiple threads. In Windows, we have a Win32 API for this. In C since 2011, in C11, we have the threads.h standard library. And in C++, also since 2011, or C++11, we have a threads library, just like in C. In the Microsoft Flight Simulator WASM environment, however, this is not supported. There is no multi-threading possible. This is why I restricted myself to not using multi-threading. But if we have applications that try to ignore this, sometimes that makes for pretty messy code, and I have seen some very messy examples of this. So let's take a look at our application with the SimConnect library. And the simulator sends us a message, and this message then comes into the queue, where we need to decide what to do with that message. We might have handling methods for open, quit, exception, system state, events, or object data. In this case, for example, it could be something for handle system state. We still need to do things with that. For example, with system state, we might have multiple requests for that, and we need to decide which part of our application needs to get the contents of this message. The same, of course, is for handle event. That also might have different parts of the application that need to know that the event came in. And the same, of course, for our sim object data. So what do we do if our application has all those different options and everything is coming in at the same time? Well, we might get a problem with the queue. SimConnect has a queue, and that queue is limited. So what do we do when we don't know if the queue is full? The documentation in the SimConnect SDK just simply says it is important to call this function sufficiently so frequently that the queue of information received is processed. That's nice, but it doesn't give any guarantees. It doesn't tell us anything. So what can happen if we get too much messages? We don't know. It might be an error. It might be that the application crashes. It might be that messages are being dropped. We simply don't know. I haven't tested it. I think I'm going to test it sometime in the future, and I'm simply hoping for a little bit of spectacle. So if we cannot or choose not to use multiple threads, we must ensure our main task has planned moments where we can check for incoming messages. At these moments, we can either process all available messages immediately or copy all available messages to a local queue so they're gone from the SimConnect internal queue and process them later. This may be a bit of a puzzle because now we need to balance how much time can we spend between pulling messages from the queue, how much time do we need to process the individual messages, and how fast do we need to get back to our main task. And remember that we don't own the memory SimConnect uses for those messages, which is why I said copying all available messages. If we just copy the pointers to those messages, then when the next message comes in, it might be that our data has been overwritten with something else. So we need a cunning plan. What period have we specified? Even if we use only when changed, a small epsilon again can cause an increase in the volume of data that's coming in. Depending on the kind of data that we've been requesting, we can do things like summarizing. If we haven't processed the data, the last message yet, then also we might simply be able to afford to drop some data if we can't keep up. We cannot peek in the queue and only pick up specific messages. So we must be prepared for any type of message at any time and do something with it. SimConnect can do a bit of buffering, but how much is unknown. As I already said, the docs just state we need to dispatch sufficiently frequently. So if you can, consider going multi-threaded. It has several advantages because now you can check for and process messages in the background. You can even do things like keep lost connection logic out of sight. You can use separate threads for processing those individual messages. C++ has a lot of support for dealing with concurrency and also with concurrent updates. Yes, it takes a little bit of extra work and a little bit of skull sweat to make that work correctly, but if you take that time, it gives you a much cleaner application. Code that requests data can now block until it arrives. The word block tends to make people nervous, but it isn't always bad. We can even use things like stream processing on data using the observer pattern. If you don't know the observer pattern, it mostly just means that you use those callbacks. So, wrapping up for today. Today we looked at making request data on SimObject easy. But we found out that's not always easy for the library writer. The C++ library is already capable of most of what we want, but the devil, as always, is in the details. This current lesson took way too long to prepare, and some of that was due to me wanting to make things look too fancy. I'm currently using PowerPoint to do some of those animations, but as you noticed, it doesn't always work as I want. Google Slides, which I use for making my notes, kind of disappoints in that aspect. I looked at doing it in DaVinci Resolve, my video editor, but that opens up several large cans of worms, so for the time being, I gave up on that one. I just need to teach myself to be stricter in making shorter episodes, so I won't take too much time for making these episodes. So, next time we continue with request data on SimObject type, which is related, but now it's important to take care of extracting the object ID from the message because we can receive data for different objects. For example, different aircraft, different helicopters, or different cars, and you can specify what kind of type you want. As always, I make these videos for the subs and likes, so if you like it, please leave one of those. And I'll see you in the next one.